So hello everyone, and welcome to this webinar series on Beyond Diagonal RIS. This is part of our special interest group in IEEE Communication Society on Beyond Diagonal RIS. My name is Bruno Clerks. I'm a professor at Imperial College, and today we have the privilege to have Dr. Onel Alcaraz Lopez from University of Oulu. Will be giving this seminar on BD-RIS. So Onel is an associate professor at the University of Oulu. He got his education in Cuba, Brazil, and Finland. He had a number of appointments around the world, a number of research visiting positions. He received some best paper awards. He authored a few books on WPT and low latency communications, and is an associate editor of TCOM and wireless communication letters and communication letters. And his research interest includes a broad range of topics, including IoT, energy harvesting, wireless power transfer, wireless connectivity, machine type communication, sensing, and positioning. So before I hand it over to Onel, I would like to remind you a few rules. So the talk will be approximately 15 minutes long, and then we're going to have a Q&A session. Please mute yourselves. If we hear you, we're actually going to mute yourself. We're going to mute you. If you have any questions, please type your questions in the chat. You will also have a chance to ask questions at the end of the webinar. And that's it for today. Enjoy the talk, and Onel, the floor is yours.
Thank you very much, Bruno. I think I need to share again, right?
Yes, now you can share the screen.
Let me share my screen. Okay, so thank you very much once again. The talk will be focused on bidirectional, like beyond diagonal RIS for radio frequency wireless forward transfer. We will be covering some basics of the radio frequency wireless forward transfer technology and also about BD-RIS. And we will go directly into waveform and beamforming optimization for this kind of setups and discuss some interesting results and get some insights from them. And by the end of the talk, we will be summarizing the talk and also give some ideas for future research related to this topic. So Bruno was introducing me quite well. I'm an associate professor at the University of Oulu in Finland. And I'm associated with the 6G flagship. So if you are not very familiar with this project, this was like the first 6G project worldwide. So we were the first into 6G research, and we have quite quite interesting results as a product of this project. And you can go and visit the website. I just want to bring this up here. The project is ending by middle next year, and it has been running for almost 8 years so far. So the talk today will be mainly based on two recent publications on the topic of Beyond Diagonal RIS for radio frequency wireless forward transfer, one conference paper from WCNC, and the extension that was presently accepted at TWC. So if you want to know more details about the things we'll be discussing here, you can go to these works. Most of the details are there. So let's start with the background. So there are many technologies nowadays for wireless charging, as you can see in the table here, and they all are gaining momentum as alternative to the traditional approaches that require periodic manual recharging or replacement operations. Also, these wireless solutions aim to minimize the environmental e-waste challenge that is posed by battery disposal and replacement operations. So you can see that the wireless charging solutions can be mainly classified into ambient energy harvesting, which is also termed energy scavenging, and dedicated energy harvesting or wireless forward transfer, basically. So in the case of wireless forward transfer, the energy signals are purposely sent for charging the receivers. And all these solutions have their own pros and cons. In the case of radio frequency wireless forward transfer, which is the main focus of the talk, the main benefits are that it allows for small form factors. This is basically because the same RF circuitry that is used for wireless communications can be used and reutilized totally or partially for radio frequency energy harvesting. And also, this technology allows to natively support multi-users because the same radio frequency signal can be harvested simultaneously by several devices. So basically, there is no interference issues. And this is true for both ambient radio frequency energy harvesting and radio frequency wireless forward transfer. And the only distinction is basically that for radio frequency wireless forward transfer, we have more control over the process and can tune it at will. So we are allowed to, in general, the technology allows to transfer larger amounts of energy than in the case of ambient energy harvesting. Still, the efficiency is inherently low, and there are critical issues related to health and limitations that must be taken care of, must be taken into consideration, basically. So this is the end-to-end architecture of a basic radio frequency wireless forward transfer system and one-to-one. So there are three main components. There is the transmit side, which are basically composed by the energy transmitters, the channel, and the energy receivers. And we illustrate some building blocks within each of these components. For instance, for the transmitter side, which can be already used for communication processes. It can be a node like a base station or Wi-Fi AP, or a node specifically designed for wireless forward transfer. The signal is first generated in the digital domain, up converted to analog, up converted, and amplified before transmissions, before transmission over the antenna array. And then the signal is affected by the channel impairments, reaching the ER significantly attenuated. In the ER, which is basically the energy receiver, the signal is captured by the antenna or antenna array and rectified. And in the case of multiple antennas or rectennas, some sort of signal or energy combining mechanism is needed. And then there are the signal conditioning blocks there to improve the charge delivered to the storage or to the load. And that's it in general terms. So the main thing to note here is how there are many different sources for energy consumption and energy loss across the end-to-end chain. In any case, the channel impairments are certainly the ones that are more challenging because the losses here grow exponentially with the distance between the transmitter and the receiver. So this makes energy beamforming a highly required technique for reaching the energy receiver effectively. But we will be elaborating on this also in this slide. You can see here again the same system components, the transmitter, channel, and receiver. At the transmitter side, there are several strategies like efficient design of the power amplifiers, the charging scheduling, and the waveform and beamforming optimization. All these can be used to boost the system performance. And as I mentioned before, the energy beamforming is crucial here for compensating for the channel losses, which are the most prominent in this kind of systems. And we will soon see what is the impact of the waveform optimization later. But in general, some kind of energy efficient and low complexity transmitters are preferred. And this includes, for instance, the recently researched radio stripes networks, movable antennas, dynamic metasurface, and RIS-based transmitter as well. Why? Well, because they save energy while doing their intended tasks. In the case of movable antennas, they also offer another important degree of freedom, which is to reduce the distance-dependent channel losses. So we get closer to the receiver so we can save energy by doing that. The wireless channel, well, here the scenario geometry is something that we can sometimes influence at the deployment or by using UAVs, for instance. Yes, so this is something we can work with. At the receiver side, there are different potential multi-antenna receiver technologies that may be used, and they also determine the kind of receive beamforming that we can use. And there is also the possibility for antenna design itself, which ultimately determines the reception conversion efficiency. For instance, in the image here at the bottom of the slide, you can see the typical architecture of an energy receiver with the antenna rectifier block comprising the diode and the low-pass filter and the energy storage for the load. And the harvested power grows quadratically with the current delivered to the storage or to the load. And it is well known that this leads to a nonlinear, non-decreasing function G of the radio frequency wireless power, of the radio frequency power impinging the antenna. Sorry. So basically, the harvested power grows with the well, it doesn't decrease, grows or remains constant with the RF power delivered to the antenna, to the receive antenna. But the specific shape of the function G depends on the signal waveform. So this is the most important thing. So if one fixes the waveform, it is safe to say that maximizing the RF power maximizes also the DC harvested power. However, when we are assessing the impact of the waveform, we cannot use this kind of generic model because the function G itself depends on the waveform that is being used. But before, let us conclude with the diagram with architecture by indicating the last block, which is the load, and this is the one consuming the DC power. This block can also be resource managed somehow. How? Well, by using some kind of efficient scheduling of the device tasks and also managing their energy consumption sources as well. In general and overall, the end-to-end energy transfer efficiency depends on all these blocks. So the transmit efficiency, the channel efficiency, the receive efficiency, and also how well we are using the energy at the load. Let's go back to the waveform dependencies. So here is an equivalent circuit of a simple energy harvester. So in this case, the receive antenna is modeled as a voltage source, which basically is represented with this equation given here as a function of the receive signal Yt. And then there is a single diode, a single capacitor working as a low-pass filter, and a simple resistive load. The harvested power, pH, is proportional to the load's voltage square, as shown here, and also to the current square. So to obtain a model for V out as a function of the received signal Yt, one must carefully use the circuit's loads, including the diode's equation, and then one will be able to obtain a relationship between the signal, the impinging signal Yt, and the voltage at the load and the harvested power. Here it is such a such equationing. Basically, the IDC, the DC current is equal to this expression here. This is using some of the, let me see. So this comes basically because the diode is a nonlinear device, and then we need to use the diode's nonlinear equation. BD is the voltage across the diode. IS is the reverse bias current. BT is its thermal voltage, and NF is the ideality factor. So maximizing pH is equivalent to maximizing the output DC current. And this is the expression for the IDC current. And the expression, which was obtained like around 8 years ago or so, shows that the DC current doesn't only depend on the impinging RF power, but also on the four higher order terms of the signal YT. You can see here that it is expressed in the form of a summation of even order terms. Like the square term is the RF input power, then there is the fourth term, and so on. In practice, this has allowed obtaining important results in terms of the waveform configurations, such as these results that we are showing here. For instance, how to allocate the powers across the different subcarriers in the multi-carrier system. And the results here reveal that the optimal allocation is such that it produces high PAPR waveforms. So high peak to average power radio waveforms like the one in the bottom figure. This is something that one can expect, and also that has been well observed in practice. And basically, this is to align with the behavior of the charging cycles of the capacitor in the low-pass filter block. And this is completely opposite to communication-oriented designs where high PAPR signals are to be avoided. And again, this has been well researched in the community so far. Let's conclude this introductory part with some remarks about the RIS, and especially beyond diagonal RIS for radio frequency wires forward transfer. So it is well known that RIS provides several benefits, like enhanced efficiency, in this case, transfer efficiency, by creating a RIS-aided charging zone. It can avoid blockage, creating like virtual loss links, and also some kind of advanced waveform tunability. And this is important, as we saw earlier, because proper waveform design is important for maximizing the efficiency of the energy conversion at the receiver side. So these are very well known in general for RIS in general. In case of beyond diagonal RIS, the research has focused largely on its applications for wireless communications, showing that more degrees of freedom in wave manipulation can be obtained. This is because it can combine, redistribute, and route signals across ports and manipulate both phase and amplitude in a coordinated manner. So this allows realizing a much broader family of transformation matrices. It also brings superior performance and beamforming and energy focusing capabilities, which is good for suppressing interference more effectively and improving channel conditioning in MIMO systems. There is also the fact that it provides enhanced performance in rich scattering and endless channels. And basically, this is because beyond diagonal RIS can create channel transformation that exploit the spatial and angular diversity of multipath. In pure line of sight systems without coupling, however, beyond diagonal RIS and diagonal RIS perform similarly. This is as it is. Also, there are multiple RIS modes: reflective, transmissive, hybrid, multi-sector, and beyond diagonal RIS is also a general framework that includes all these modes. And it also can improve the robustness of hardware constraints because the designs can be a bit less sensitive to quantization or limited phase resolutions and can degrade more gracefully under circuit imperfections. But the application and configuration of beyond diagonal RIS for radio frequency wireless port transfer is much less explored, with only a few works, among which are the ones that I indicated earlier on the basis for this talk today. And in the rest of the presentation, I'll be focusing on this aspect specifically, especially on whether beyond diagonal RIS can enhance radio frequency wireless port transfer beyond what diagonal RIS can, and when and how, basically. So let's go to the core technical content and discuss about waveform and beamforming optimization of radio frequency wireless port transfer assisted by a beyond diagonal RIS. So let's use a very simple system model. So we consider a SISO wireless port transfer system with a beyond diagonal RIS consisting of M elements. So here we assume there is no direct path between the energy transmitter and the energy receiver. And this is important because by excluding the direct link, we can isolate and highlight the contribution of the RIS to the overall performance. So this allows like a fairer and more focused comparison between different RIS architectures. But I think all the algorithms and discussions we have here can be extrapolated to the case where we incorporate the direct path as well. And I think the paper, we also indicate how to do this specifically. So in this case, we adopt a multi-tone waveform. This is motivated by the ability to exploit the rectifier nonlinearity to improve the performance, as we discussed in the previous slides. In this case, there are n equally spaced subcarriers, tones, and they are equally spaced as shown in the top equation here, and also Fc is the initial frequency, which is basically the same as F1. At the bottom of the slide, you can see the transmit signal, which is a superposition of the tones, where Sn is the complex weight of the nth subcarrier. In the figure, we can also see the incident and reflective channels for the nth subcarrier, which are denoted as HIN and HRN. And for simplicity, we also assume that there is perfect CSI knowledge. So in this case, the scattering matrix theta is given by this, where zeta 0 is the reference impedance. And below, there are two extreme cases of in this case, to the left, there is the fully connected beyond diagonal RIS, and the right side, there is the typical diagonal RIS in the case of four ports. So you can see in the case of fully connected RIS, all the elements in the matrix Z can be non-zero, while for the other sub-architecture, some of diagonal entries may become zero. And in the case of the diagonal, well, Z becomes a diagonal matrix. That's how it is. Let me see. Here I missed discuss about the last part, and is that in the case of reciprocal and lossless beyond diagonal RIS, the scattering matrix is symmetric and unitary. So this is captured by these two constraints at the bottom. So we are considering the case of non-mutual coupling here between different ports. This is basically for simplicity and easy to handle. So HN here is the cascade channel at the end to carrier. And the received signal then can be written as YT by this summation of the end tones impacted by the channel. Now it is time to remember that the harvested power increases with the direct current, which is basically this summation here. In practice, it is often enough to take only the first two terms because those are the ones that impact the most. The others are usually negligible. And the main approach we adopted here is that noticing first that using this kind of expression requires averaging over time samples, which makes the optimization extremely challenging because one would need to consider a high sampling rate for achieving sufficient accuracy. So instead of using the time domain, we transform it to the frequency domain. And this expression transforms into this in the frequency domain. So in the frequency domain, it's easy to see also here that the last term is the one related to the fourth order of the signal, and is the one that captures the intertone impact, while the first term focuses only on their individual power coefficients. So it's basically the one related with the RF power, the first term. So with all this in place, we can already formulate the optimization problem, and it's basically with the goal we pursue here is to maximize the direct current delivered to the load under the constraints imposed by the beyond diagonal RIS, and there is a power budget at the transmit side PT. And the goal is to optimize the waveform coefficients Sn and the scattering matrix theta, the BD-RIS. Here, I think one remark is that the power consumption of beyond diagonal RIS scales with the number of interconnections between the ports, which increases the circuit complexity and the overall power consumption compared to traditional D-RIS, but we don't focus on this here. So we assume that there is enough power at the RIS to be operational independently of whether it's a diagonal RIS or beyond diagonal RIS. So let's go to some solution approaches for this problem. So as typical in these kind of frameworks, we isolate the waveform and beamforming problems, leveraging alternating optimization. So the idea is to solve first the waveform optimization problem, given a scattering matrix, and then this produces the tones coefficients, and then fixing these coefficients to solve the beamforming problem afterward. So I mean finding a new scattering matrix theta and so on. So we resolve these problems iteratively. And this is because basically handling the two kinds of problems at the same time is not like an easy at all task. And also in practice, it would make sense because these variables are a different kind of network elements. One is at the energy transmitter and the other is at the beyond diagonal RIS. So it makes sense also in practice that some kind of iterative procedure between these. They are naturally separated anyways. So focusing on the waveform optimization problem, which is the one at the bottom left, we can first note that this is a non-convex problem because IDC here is convex with respect to the signal coefficients Sn. So the constraint is convex and the objective function is convex, but then we are aiming to maximize a convex function. So this is not a convex problem, but this kind of problem is can be well resolved using successive non-convex approximation, SCA, because it can solve the problem ultimately for this kind of non-convex problems. So in fact, we obtain a very simple iterative procedure using SCA for this waveform optimization. And it is in closed form. I will not go obviously over how this was obtained, but it's using KKT conditions. And for this iterative procedure, one can use a simple scale match filter for initialization. So this is for the waveform optimization part. So the first problem. The second problem, the beamforming optimization, is somehow more challenging, and is the one that we will be focusing in the next few slides. And we will be discussing some different approaches to solve. And this is because this is the problem related with the RIS, because the beamforming is occurring there. So the first solution for the beamforming optimization is based on SDR. In this case, this solution framework is proposed only for fully connected beyond diagonal RIS. The main challenge here is that the matrix theta is non-diagonal, is a non-diagonal scattering matrix that must be both symmetric and unitary. So the first step is to write theta in a more convenient form. In this case, we use the permutation structure. So we vectorize it into a single optimization variable theta, lowercase. This allows us to express each cascade channel Hn as a simple inner product between An and the theta lowercase. You can see the definition of An here as well. Basically, it's a function of the channels and the permutation matrix. So to deal with the nonlinearity harvesting model, we lifted the lowercase theta into a matrix X. So this will replace the quadratic terms with a linear trace expression and turns the unitary constraints of theta into linear constraints on X. So basically this leads to this kind of problem here. So this ball phase K0, you can see it to the right. So it's just a diagonal matrix of the K4 coefficients. Remember that K2 and K4 are coefficients related to the energy harvesting model. K2 is the one related to the RF power, and K4 is the one related to the fourth order term of the signal. So K0 is positive semi-definite. So the objective function is convex. And the problem is therefore a non-convex problem because it deals with the maximization of a convex function. Also, there is a rank 1 constraint. But the first issue can be solved again using SCA. And the second one, the rank constraint can be resolved using relaxation. So this leads to the standard semi-definite relaxation program that is shown here, which can be solved very efficiently with SDP solvers. In the case the SDP solution happens to be rank 1, then we recover theta exactly, so optimally. If it is higher rank, then we need to use some kind of approximation. In this case, we can use Gaussian randomization and project the resulting candidate back on the unitary manifold using FBD. So this step is important because it allows the final theta to be feasible for a real beyond diagonal RIS. This is a very accurate result you can see later on and offer often near optimal, but it only applies to fully connected beyond diagonal RIS, and this is because basically it deals directly with theta as an optimization variable. The main difficulty is that requires high computational cost, and therefore it is best suited for RISes with a moderate number of elements. A lower complexity solution, also for the case of fully connected BD-RIS, is to apply SCA directly to the problem in the original form. In this case, one can linearize the objective function using the Taylor expansion, which is the typical approach for SCA. And the main challenge still it is the unitary constraint. And in this case, we handle it splitting in two parts. The left one, the left side is convex and can be written using the short complement, while the right side is non-convex, and we can linearize it around the current iterate using the first order Taylor expansion as well. So this gives us a local convex approximation of the feasible set. You can see here that we had to introduce an auxiliary variable S to prevent basically the optimization from becoming infeasible when the linearization is not yet accurate. So with all these elements in place and combined, each SCA iteration becomes a standard convex problem. It's the one shown here. And two things to notice here are that to ensure numerical stability, we had to impose a trust region on how much theta is allowed to change at each iteration. So basically, this is the last constraint. This is to allow for a smooth transition and not, to change smoothly over the iterations. Also, the trace of S is penalized in the objective function because you remember that S is a slack variable, and basically it was introduced to ensure feasibility while looking for the solution, and it should ultimately go to 0. And then the outcome is gradually refined such that it remains close to the unitary set and converges to a feasible beamforming configuration after a final projection step. So compared to the SDR method we saw earlier, this SCA-based method approach avoids the rank 1 lifting and is also faster and better suited for medium-sized, fully connected BD-RIS deployments. Still, it's only applicable for fully connected BD-RIS because we are again operating directly on the scattering matrix without any other constraints. And finally, the last approach we propose is applicable for any kind of a structure because the idea is to optimize directly the impedance matrix Z, and then we know what is the construction feasible based on Z for the scattering matrix theta. And this is basically captured in the last constraint here in this problem. So that's it. The main challenge, nevertheless, is that Z appears inside an inverse when forming the scattering matrix, which then is difficult to handle because this theta is the one that affects the IDC. So to make the problem tractable, we linearize this inverse using a first order Newman series. This is shown here. The approximation of the inverse is quite accurate, especially when the updates to Z are small. And this is something that we enforce through an adaptive step size mechanism. So once the inverse is linearized, the cascade channel becomes an affine function of the of a perturbation matrix omega. So we collect the entries of this omega uppercase into an omega lowercase vector. And this is useful because the harvested DC current becomes convex with respect to this lowercase omega. So this allows obviously to apply the same first order Taylor approximation and use the SCI procedure once again for this case. So the main thing is that after transformations, the problem becomes the one shown to the right. So the first constraint is to guarantee that the Newman approximation remains valid. And the last constraint ensures that the omega has the same 0 entries as Z, depending on the structure of the BD-RIS. In the case of a fully connected BD-RIS, obviously this constraint is not needed and we can remove it because we don't have really constraints there. And solving this, we have again a simple KKT-based closed form update for W in each iteration, and then we can use this to construct the impedance matrix Z accordingly, and then obtain the scattering matrix. Overall, this whole procedure is quite lightweight in the order of requiring M squared, with M is the number of RIS elements. M squared operations is instead of M4 and M6 that is required for the SDP. So the method incorporates the BD-RIS structural constraints by forcing some entries of omega to 0, which means it works for fully connected, group connected, tree connected, and forest connected architecture or any. So now that the algorithms were discussed, we can analyze the main results and main insights from this. So this is the simulation scenario we adopted. We use set the frequency operation to 2.4 gigahertz, use a bandwidth of 10 megahertz. Since n is the number of tones, we use the intertone spacing as bandwidth divided by n. As for the path loss, we assume quadratically dropping power with the distance and a reference power of minus 40 dB at 1 meter distance. So the RIS elements are positioned on a uniform planar array with lambda over 2 separation between consecutive elements. For simplicity, we consider a symmetric setup where the incident and reflected path lengths are equal to 2 meters, while the elevation and azimuth angles are set to pi over 6. So the energy harvesting receiver has parameters K2, K4 equal to this that you see here. And remember that these parameters represent the contribution from the second and fourth order signal of the signal components. Also, the channels are modeled using quasi-static Riccian fading, where kappa is the Riccian factor. In the case of the loss component, is fully geometrical. So it basically depends on the relative position of the transmitter receiver and the RIS elements. For the n-loss part, we use a Rayleigh fading considering L equal to 18 delay taps with realizations following circular symmetric complex Gaussian. We also introduced an additional parameter alpha for the n-loss part. In this case, alpha multiplied by the bandwidth gives you the coherence bandwidth. So selecting a small alpha such that coherence bandwidth BZ is much smaller than the bandwidth leads to more frequency selectivity, the channel, while a large alpha leads to a coherence bandwidth that is much larger than the bandwidth, which means all delay taps can be received within the coherence bandwidth, leading to a coherence flat channel. The powers and time delays of these tabs are generated to satisfy these assumptions. So the figure here compares the performance of the proposed algorithms for a fully connected BD-RIS as a function of the number of tones n. And in this case, it is shown that the SDR approach achieves the best performance. This is done with the frequency selectivity of corresponding to alpha equal to 0.1. So there is certain frequency selectivity here. M equal to 16 elements, and the transmit power is 50 dBm. So the performance is SDR outperforms SCA, which outperforms the last and simple iterative procedure. But remember that this is at the cost of higher complexity, much higher complexity. And the performance also increased with the number of subcarriers n. I forgot to say that. So let's see the waveform here in the right side, in the time domain. This is generated, these time domain signals are generated using the SDR approach with a power of 50 dBm at the transmitter, and alpha equal to 1 and 10. So alpha equal to 1 is there is frequency selectivity, alpha equal to 10, and there is no frequency selectivity. We can observe how the waveform has high PAPR, as discussed earlier, even for low alpha. So that means selective channels. And when the power of the transmitter reduces to 30 dBm, so 20 dB less, the PAPR of the optimized waveforms reduces. So especially for a small alpha, even for a small alpha, the effect cannot be appreciated much. So this is somehow agrees with the earlier remark that the fourth order term of the signal components becomes significant only for relatively high powers. Otherwise, this fourth order term is very, very small, so it doesn't affect. Overall, the high PAPR signals are beneficial to leverage the rectifier's nonlinearity, are beneficial for that. And you can observe for especially when the received signal is sufficiently strong. And let's continue with this such strong signal of corresponding to a 50 dBm transmit power. In this case, we represent the normalized gain of the channels and input signal for different values of alpha for a given channel realization. So for alpha equal to 0, 1, 1, and 10. We can see, and the channels that are representing the figures are the input signal, or the relative importance or relative weight of the input signal, the cascade channel, the incident channel, and the reflected channel. We can see that the variation among the gains of the cascade channel at different subcarriers, which is in the x-axis, becomes smaller as the incident and reflected channels becomes less frequency selective, so increasing alpha. And this is caused by the nature of the frequency flat channels, where the channel values at different subcarriers are almost equal. So the BD-RIS configuration impacts them all similarly. However, when the channel becomes more frequency selective, the BD-RIS configuration impacts the independent channels at different subcarriers differently. Also, the power allocation pattern among the different subcarriers of the input signal also changes with this alpha. In this figure, we show the average IEDC as a function of the number of subcarriers n. In this case, for bidirectional RIS, for beyond diagonal RIS and for diagonal RIS. And you can see that both RIS architectures achieve the same performance for any n under loss. while for the regional channel with n-loss components, and the BD-RIS outperforms the diagonal architecture, and the gap also increases with the number of subcarriers. We also plot here the performance as a function of the number of RIS elements, n for two configurations of n equal to 1, which is the single-tone transmission, and n equal to 4, with some waveform degrees of freedom. And in the case of full loss, and both BD-RIS and D-RIS achieve the same performance, we can see that this is nothing to do with m. So everything is okay up to there. Meanwhile, under the influence of some non-line of sight, as in the right-hand figure, BD-RIS can leverage the extra degrees of freedom to impact different channel components more effectively, such that the IDC becomes higher compared to the case of D-RIS. Also, the performance increases with the number of RIS elements due to the beamforming gains of the RIS. The gap between BD-RIS and RIS increases also with M. So that was the main technical core of the presentation today. Let's conclude with some remarks and some potential research directions. So overall, we formulated a joint optimization, a joint beamforming and waveform optimization problem. The idea was to maximize the power that the radio frequency energy harvesting device can harvest from a base station through a beyond diagonal RIS. So this kind of problem is usually handled by decoupling the waveform optimization and beamforming problems, and also using then alternating optimization, which is exactly what we did here. The waveform optimization is only transmit dependent, so it's easier to handle, and we propose an efficient iterative method for it. In the case of beamforming, this is RIS dependent and obviously more tangled, especially for beyond diagonal RIS. And in this case, we propose three beamforming approaches, relying on SDR, SCA, and one fully iterative procedure. So from bottom to top, they provide better performance, but at the cost of much higher complexity. And in all the cases, the complexity scales to some degree with the number of RIS elements, as is expected, and also with the number of subcarriers. So we proved also that beyond diagonal RIS achieves the same performance as diagonal RIS under loss conditions. This is all in the absence of mutual coupling, while it outperforms diagonal RIS in the case of non-line of sight affectations. Also, our findings demonstrate that the frequency selectivity of the channel impacts the way that the beyond diagonal RIS shapes the cascade channel. And we show that the waveform power allocation to different subcarriers depends on the transmit power and the rectifier operations regime, which aligns with some results already in this regard in different setups. Some key research directions we feel that are worth pursuing are these ones that are indicated here. First, extending the simple size scenario to a MIMO and even multi-user MIMO with multiple receive devices or multiple coordinate base stations as well. This is something that is an obvious extension of this work. And this is crucial here for better spatial multiplexing and user selective power focusing. In this case, the multi-beam, multi-user energy precoders and optimized RIS scattering responses must be designed to ensure scalability as both the number of users and RIS elements growth, which is quite critical and difficult to achieve, in fact. Another important direction is considering the impairments and costs associated with the use of the RIS technology. This includes, for instance, modeling the power consumption and also the mutual coupling. Recall that we said that the BD-RIS tends to require more energy consumption than its diagonal counterpart. So what would happen, for instance, if this RIS is also powered by an energy harvesting source? So we have limited energy resources, or if it is even powered by another wires forward transfer process, would this kind of beyond diagonal architecture would still be preferred here? It's an open question. Another research direction, the third one, is related to the potential of BD-RIS for simultaneous wireless information and power transfer by shaping both the energy and the information streams. One may make some beams maximize, for instance, the harvested power, and others preserve their data reliability. But some work is needed for resolving the power information trade-off through an RIS aware waveform design, coding, and resource allocation in general. And last, the BD-RIS can also serve as a reconfigurable meta-sensor, so enabling the environment awareness while supporting also the wireless power transfer process. So one may reconfigure the RIS to generate dual-purpose waveforms that deliver energy while enabling localization or channel tomography in general. For instance, taking advantage of BD-RIS to enhance the near-field sensing and detect obstacles or living spaces for safety and adaptive beam control. This may be done simultaneously or sequentially. This remains to be seen. And I think this direction is also very important for autonomous and intelligent wireless power transfer systems. And that was it from my side. Thank you very much for attending. And if you have any questions, I would be happy to take a few.
Thank you very much, Onel, for the interesting talk. Any questions from anyone? I don't see any question in the chat so far. I have a question for you, Onel. Do you have any insight on the optimal BD-RIS architectures for WPT? Especially accounting for this non-linearity, because we have some understanding of tree connected and forest connected and stem and band connected. Would those architecture change if you have non-linearity? What are your thoughts on that?
Yeah, thank you very much, Bruno. I think that's a very important question. If you look at for the non-linearities alone, I'm not fully sure. Maybe you can we can have your thoughts on that. What I know that is that in these cases, something that has not been explored that much is the complexity and energy consumption that this new interconnection bring. And this is crucial for this kind of setups where we have radio frequency wireless power transfer, where efficiency and energy consumption are key. If you look only at the energy harvest on the ER side and the energy consumption of the ER side, that might not be that important. But if you have a look at the whole system and how it can be sustainable or operated, take into consideration the architecture and the complexity it brings and the new energy consumption sources that it brings is important. And that's why I identified this as a research direction here, as a second important research direction. So what if we consider these energy consumption sources? What if this energy comes from the impinging signal as well, and then we need to use it? So for a fair comparison between architecture, I think this is crucial to take into account. As for the way in which the signal is handled, I suspect that the more the more the degrees of freedom you have, the better you can control the signal, right? And reach the receiver with the intended signal waveform. I don't know if that answers your question.
Yes,
or if
that's
you have
right.
any insights.
Yeah, Yeah, I mean, we don't need all interconnections, right? In theory, you may know the tree connected and the band and the stem connected. We don't need all interconnection to achieve optimal performance. I mean, those are sufficient conditions. Tree connected is optimal to achieve the same performance as fully connected if you transmit one stream of information.
Okay.
It's sufficient condition for achieving exactly the same performance, but it has much lower number of tunable element and therefore potentially power consumption also. But I don't know whether actually in WPT, because you have nonlinear response, whether actually you could have other types of BD-RIS architectures that actually would.
Yeah, that's something we haven't
perform better.
We haven't put effort into that, but it seems like something that it should be done, certainly.
Okay, thank you very much. Is there any other questions from anyone?
If not, you are free to reach me over email, and I will be happy to take any questions over there.
Okay, great. Thank you so much, Onel, for your great talk. Thank you everyone for attending.
Thank you very much.
And see you in our next webinar. Thank you very much. Bye-bye all.
Bye-bye.